Thanks. Thank you, Kalina. I'd like to thank the organizers for having me here. And actually, the one person who I would like to thank the most is unfortunately not here now. That's Andrew Wade, who I somehow also work with and who invited me to this beautiful event. I had a really great time in the past 2 weeks, and okay, I'm leaving today after tomorrow. Okay, so I'll be talking about this convex hull of planar Brownian motion, and it's a joint work with Wojciech Cigan from Wrocław and Hugo Panzo from St. Louis University. Okay, so let's introduce the object that we'll be dealing with throughout the whole presentation. So we have just the standard planar Brownian motion, which is the ordered pair of two independent standard one-dimensional Brownian motions. They all start at 0. With the con of A, we denote the convex hull of a set, so the smallest convex set containing the set A. And so the object that we are interested in is the so-called Brownian convex hull. Okay, so we take the trajectory of the Brownian motion and we just make the convex hull of that trajectory. Okay, so how does it look like? Let's say this is our Brownian motion and that's its convex hull. Okay, and we are interested in the size of it. So what do we mean by size? Well, we studied several different geometric functionals. I mean, several of them were already studied, like perimeter of this thing. So yeah, the perimeter, it's clear what it is, the area of this hull, the diameter of the hull. And then we also, just for fun, also studied the circumradius, which is the radius of the smallest circle that can be circumscribed to the whole hull, and the in radius, which is the radius of the largest circle that we can inscribe inside the hull. Okay, and okay, so let's see what has already been done before. So the notation, sorry. So the notation is just P for perimeter, A for area, D diameter, big R for circumradius, and small r for in radius, and we drop the time when t is equal to 1. Okay, so when it comes to the perimeter of the Brownian convex hull, this problem of what is the okay, so when we let our trajectory run, then we make this convex hull, we have some random set. Then when we attack this random set with these functionals such as perimeter, area, and so on, we get some random variable. Okay, and of course a lot of different questions can be asked about these random variables, but we are only interested in expected values. Okay, and also when it comes to Brownian convex hulls, people are interested in much different questions like the smoothness of the boundary and things like that. We are only interested in these geometrical functionals of the hull. Okay, and so in 1972, Letak posed this question about what is the expected value of the perimeter of the Brownian convex hull in the American Mathematical Monthly. And 2 years after, again in American Mathematical Monthly, it was sold by Takash, and he showed this beautiful result that the expected value of the perimeter of the Brownian convex hull is just square root of 8 pi. Okay, and I'll show you a little bit of details because it's simple, and like in the background of these things are these beautiful Cauchy integral formulas. And in planar case, so in 2D, there are Cauchy integral formulas for both perimeter and area, and those are actually the only functionals for which there are just closed expressions, not just bound, but closed expressions for those geometric functionals. Okay, so Cauchy surface area formula, yes?
But shouldn't that depend on t?
Yes, sorry, so I dropped t when t is 1, and so this is perimeter at time 1. Okay, so, and I will usually just run always the Brownian motion up to time 1, and I will have this one big slide that once you know the result for t equal to 1, directly from Brownian scaling you have it for, so like in general for t, so at time t, there will be still t under the square root, so it will be square root of 8 pi t. For area, of course, we would multiply with t, and for all the other functionals, since they are also linear, it would just be the square root of t would appear. Yeah, I'll just comment briefly on that at some later point. But from Brownian scaling, we just show that, yeah, we just have that it's enough to study it at time 1. Yeah, but when only a letter without any time appears, it means the time is 1. And most of the time is 1. Like throughout the whole presentation, the time is fixed to be 1, since it's anyway not important. Okay, so there is this Cauchy surface area formula. In general, it's a known result for the surface area in d dimensions. But when you restrict it to 2D, then the surface area is exactly the perimeter. And so this formula says that if we integrate from 0 to pi this function w of theta, we get the perimeter. And what is this w of theta? Well, it's the difference between the maximal and minimal projection in this direction of theta. So maybe it's easier just to show it on a picture. Okay, so for every angle theta between 0 and pi, what we do, so we take the line and we project the whole trajectory on that line. Okay, so basically this first part in the definition of W was the supreme, so we find the highest point in this direction, we project it on the line, we find the lowest point, we project it, and the length of this projection is our so-called parametrized range or parametrized width. So the difference between these two projections is this thing that we then integrate from 0 to pi to get the perimeter of our hull. Okay, but what are we really doing there? So we are projecting our regardless of theta. Once we project this two-dimensional Brownian motion, we just get one-dimensional standard Brownian motion. So this parametrized width, regardless of the angle theta, is just the difference between supremum and infimum, or maximum minimum, of one-dimensional Brownian motion. Okay, so and this is a thing that we will anyway be mentioning several times. So let's introduce it. This is what's usually referred to in the literature as the range of Brownian motion. So if we take a one-dimensional Brownian motion, okay, started at 0, then with R of t, we usually denote this difference between the running supremum and running infimum, and it's called the range of Brownian motion. And this has been studied since a long time ago, and a lot is known about it. Like even the exact form of the density function of the range of Brownian motion was computed already in 1951 by Feller. Okay. And yeah, he additionally established also some results about the moments of this range. So this is again a range at time 1, and then just by using this result, we can reconstruct the result obtained by Takashi in this 1980 paper from American Mathematical Monthly, when he calculated that the expected perimeter is square root of 8 pi. Okay, because we don't really care for every theta, we have the same thing. Okay. For every theta in law, we just have range. Okay, and since we are interested only, of course, there's some dependent structure between these W of thetas, but we are just interested in the expected value, so we don't care. Okay, if the angles are if the angles are if we are talking about perpendicular directions, then we do have independence, but we'll come to that later. So anyway, it's actually relatively easy from here to reconstruct the result that the expected value of the perimeter is square root of 8 pi. Okay, and I won't go in so many details when it comes to area, because the Cauchy integral formula for the area of a planar convex set is a bit messier, so the whole procedure is a bit messier, but it's not that difficult, and it was obtained by Al-Bahir in his PhD thesis, and it holds that the expected value of area is just pi over 2, and of course at time t it would be pi over 2 times t. Okay, and that's it when it comes to closed formulas. Okay. So now only bounds are known for all the other functionals. Okay, and diameter was already studied in the literature. Okay, but one thing is that, okay, for diameter, you can imagine if this is the diameter of a set. The question is, what is the convex body with this diameter that has the smallest perimeter, and which body has the biggest perimeter? Okay, and the smallest perimeter is obtained by this particular set, just this line segment, and the largest perimeter is obtained by a disk, and okay, also these funny shapes of constant width that we don't have to go into, but we always have that the ratio between perimeter and diameter. Okay, so what is the perimeter of this line? It's actually defined as 2 times its length. Okay, and and what's the perimeter of the disk? Is of course its diameter times pi. So we always have that the ratio between perimeter and diameter is between 2 and pi. Okay, and so from this relation, for free, we get bounds for the expected value of the diameter, because we know the expected value of the perimeter. Okay, and this has been computed. So plugging this square root of 8 pi that we also developed recently into this series of inequalities, we get for free somehow a lower and upper bound for the expected value of the diameter of the Brownian convex hull. Okay, and then James McCradle and Chang Shu, who were both PhD students by Andrew Wade, they improved on both of these bounds. Okay, and what was their rough idea? So when we look at this Brownian convex hull. So what they noticed is if you project this, if you project this Brownian motion on x and y axis, so these are just projections for theta equal to 0 and theta equal to pi half, you get this, so the first component attains some range up to time 1, and the second component attains some range up to time 1. And for sure, the diameter of the hull, okay, the diameter is actually, it doesn't matter if you look at the hull or just the trajectory, okay? The diameter of the trajectory will be the same thing as the diameter of the hull. But what we know is that the diameter is definitely bigger than R1 and R2. And why is that so? Well, okay, there is some point that is projected here on this end of this line, and there is some point projected here. So when we connect those 2 points, well, we'll have at least length R1 in this. So we will have a segment of length at least R1 somewhere here. It will be even longer, and there will be the segment of length at least R2 in this direction. So for sure, our diameter will be bigger than both R1 and R2. So the range, and R1 and R2 are actually ranges of those initial W1 and W2 from the first slide. So our planar Brownian motion is ordered pair of W1 and W2, two standard one-dimensional Brownian motions. We look at the range of the first one, we look at the range of the second one. The diameter is definitely bigger than both the range of the first one and range of the second one. And on the other hand, we can fit the whole hull into rectangle whose sides are these R1 and R2, okay? So just these two trivial observations led them to conclusion, if we use these notations from pictures, R1 for the range of the first Brownian motion and R2 for the range of the second Brownian motion, that our diameter is definitely bigger than maximum between ranges R1 and R2 and smaller than the diagonal of the, so the diameter of this trajectory is definitely smaller than the diameter of this rectangle into which we fit this trajectory, and the diameter of this rectangle, of course, is just its diagonal. Okay, so this is what they started with. Okay, and so what did they do after that? Well, they actually, so they comment on the fact that already Feller knew the density function of the range of one-dimensional Brownian motion, but they comment that, like, as you already saw, the shape of the density is a bit messy. This is this infinite sum. So they decided not to work with that, okay? And then they use this known relation for the maximum, that you can just write it like this, and they further bounded this thing from below. And notice what is important, R1 and R2 are independent. Okay, one is the range of W1 and one is the range of W2, and W1 and W2 are independent one-dimensional standard Brownian motion. Okay, so they further bounded this from below to obtain a lower bound of 1.601. And then I was lucky that just by accident I found, so one funny thing about this paper, so it's in Statistics and Probability Letters. If you search for it online, you'll find this version where on the first page you have this information about when the paper was received and when it was submitted. So when it was submitted and when it was accepted, and actually it was accepted only 3 days after submission, okay, which is roughly 1 year faster than I got my responses, because 1 year is roughly 1 year longer than 3 days, yeah. So anyway, as soon as it appeared on arXiv, they started receiving some emails. Of course, I didn't know about that, but then just by accident, I found out that some people immediately found some ways to improve those bounds. And first one is Hugo, one of the collaborators on this paper that I'm talking about now. So, and I met him on Levy conference, where I also met David 2 years ago in Mannheim. And he said, okay, so he realized that if you look at this two-dimensional Brownian motion, and then if you look at the smallest circle, but centered at the origin, so it's not the same thing as looking at the circumscribed circle, like the one that doesn't have to be centered at the origin. So he just said, if we now find the smallest circle that contains this thing, okay, but is centered at the origin, of course, its radius is smaller than the diameter. Okay, that's clear because both this point and this point are inside the hull, so for sure the distance is smaller than the biggest distance between any 2 points. Okay, but what is this distance? It's a Bessel II process. We're just looking at the distance of two-dimensional Brownian motion from the origin, okay? And then this can be tackled, okay? There is some work to do, but it's just the maximum of a Bessel II process run up to time 1, and it can be expressed in relatively explicit form, and it can be calculated, for example. I mean, he used Mathematica, but numerically you can calculate it, okay, to arbitrary precision. And he did improve this 1.601, okay, so it's a better idea than what they had. And then he was tempted. He said when he saw that the paper got accepted in 3 days, so he said maybe I'll have the same luck. But then he decided after all that he didn't send it anywhere, so it was somehow hidden. Okay, and then they received another email, and I was also, just because I met Andrew Wade, who was their advisor, and he knew about those emails. I found about the email that they got from Kilian Rachel and Rodolphe Garbit. Okay, I'm definitely pronouncing their names or surnames or both wrong, in a wrong way. But they realized that it is possible to tackle this expression directly, okay? So we already mentioned that the density function was obtained by Feller, but it was not easy to jump from the density function to the cumulative distribution function, okay? And that's what McRedmond and Shu didn't manage to do, but then already Feller commented in his paper that there is a strong relation between the thing that he is looking at and the statistics from the Kolmogorov-Smirnov test. And he used this relation to even show that the density that he obtained is the density function in the sense that it integrates to 1. And using the same relation, Rachel and Garbit, they managed to find the CDF, okay, the CDF of the range of one-dimensional Brownian. And then again, okay, they had to do some numerical analysis, but they had some expression for the CDF, and using the CDF, they improved this lower bound all the way up to 1.86, okay, which was a significant improvement. But then they also thought that since they didn't improve the upper bound, it's probably not worth publishing, so they also didn't send it anywhere. And turns out they were wrong because in the end there was this lady Jovalekic in 2021 who basically did the same thing, but not with this relation to Kolmogorov-Smirnov statistic, but she recognized some Jacobi theta function in the background of this density function that I showed to you, and then she knew how to somehow integrate that to get the CDF using some Jacobi theta function tricks. And then she actually did some sloppy numerical analysis, and that's why it's actually even slightly worse than the bound by Kilian. So it's 1.856. But that's the only thing that you can now find published in the literature, this paper and this bound of 1.856. And actually, Kilian told me that since we were somehow interested in their observations, that they maybe will put their preprint in our archive. They won't publish it anywhere, but maybe their analysis, which is different, like there's a different approach, and then it's better numerical analysis, so it's slightly better at lower bound. They will maybe put it on archive sometime soon. At least they are planning to do that. Okay, so that's the story about the diameter. Okay. Not the whole story, of course. For the upper bound, we, as I said, use the fact that the diameter is bounded by the diagonal of this rectangle, and then, of course, just by we then know that the d squared is bounded by this, and we can use Jensen's inequality, and we know the second moment of the range, and that was already computed in 1951 by Feller in this paper, where he developed the density function. He developed the first and second moment. So just by plugging everything here, they obtained this upper bound. And this hasn't been improved since then. Okay. Okay, and then we started with this circumradius and inradius. But what was even more interesting to us were these inverse processes, but I'll come to that later. So, okay, when it comes to circumradius, well, this same picture can be used. So if this R is the circumradius of some convex set, again, the smallest convex set when it comes to its perimeter with this inradius is again just this line, and the largest convex set in sense of its perimeter with this circumradius is this disk. So again, we get some bounds from the expected value of the perimeter for free, okay? Just as in the case of diameter, okay? But then we managed to improve on both of these bounds. And actually, yeah, so we haven't received any emails for quite some time, so we were somehow happy. Maybe we did a good job with all the bounds because no one managed to improve. And then I will show you that we have run really, we missed one really simple. I cannot over stress how simple it was, improvement of one bound. But anyway, I'll show you our first. So now there are no more very clever ideas here. So some clever ideas will turn up when we start dealing with the inverse processes. Now here it was just some relatively simple, but for the full story, I'll show some relatively simple bounds. So we bounded in our paper the expected value of the circumradius, so with 0.93 from below and 1.2 from above. And since Kilian and Rodolphe and also the Jovalekic, they did such a good analysis on this diameter that even just this trivial observation, the diameter is always smaller than 2 times circumradius, was something that we couldn't beat, okay? So just by looking at half of the lower bound, what they had for the diameter, it was already the best lower bound for the circumradius we came up with. So it was 0 ideas and 0 calculations there, okay? And for the upper bound, so we found these bonus and type inequalities. So I will, even though this is not the best thing that one can do, I will talk about it because we will anyway use it later. So just a short excursion to these bonus and type inequalities. So I suppose you're familiar with the classical isoperimetric inequality, okay, that the p squared, so the perimeter squared is greater or equal to 4 times pi times the area, and the equality holds when this C is a circle, okay? Then this guy Bonesan developed a series of inequalities that were of this form, that p squared minus 4 pi a are bigger than or equal to some b. Of course, this quantity b always had to be non-negative. It could vanish only for a circle, and it had some geometric significance. Okay, and so we found one such inequality of this shape: p squared minus 4 pi a, so perimeter squared minus 4 times pi times area, is bigger than or equal to something. And so it turns out that it's bigger than or equal to this thing here. So p minus 2 pi q squared, where q can be anything between the in radius and the circumradius. So if you take any value between in radius and circumradius, you get this sort of a bonus and type inequality, okay? And from here, okay, you reorganize that and you get this type of bound. So you get a lower and upper bound for any value between the in radius and circumradius, okay? So we decided, okay, maybe we can use this for both circumradius and in radius, and that's what we did, okay? So we used these bounds. So this one we used for the circumradius, and for the lower bound I already showed you. We used the result for the diameter. For the in radius, we used the lower bound, and the upper bound we improved, because this gives you both bounds, upper and lower, but we managed to improve on some of them. And okay, so in particular, if you plug for Q the circumradius, you have this bound for the circumradius. Okay, so you want to tag this with the expected value, okay, and you can put this expected value under the square root because of the Jensen's inequality, but you then also end up with this expected value of the perimeter squared. And lucky for us, like the only quantity for which the second moment is also computed and appeared already in the literature. So not even for area is it known, or some higher moments for perimeter, but the second moment for the perimeter is explicitly calculated, also by Andrew Wade and by one of his PhD students, Chang Shu, and it's expressed through this relatively ugly integral. But one has to be careful with the numerical analysis, but one can integrate it numerically and get the approximate value. And so plugging everything inside here, so we know we need this expected value of p, which we know, expected value of a, which we know. We also, due to those guys, know the expected value of p squared, and then plugging everything here gives us this. But I don't know how and why we overlooked that just the same argument again as in the paper by McRedmond and Shu, that we can just, you know, squeeze our hull inside this rectangle. So of course, our circumradius is small, like 2 times our circumradius is smaller than the diagonal. Already this simple observation that the 2 times the circumradius is smaller than the diagonal of this rectangle that I showed several slides ago actually improves the upper bound, okay, to this 1.1774. Okay, so anyway, this is one stupid thing we missed, and the improvement that now appears in the newer version. Okay, when it comes to in radius, okay, for the in radius we actually did use this lower bound from this Bonesson type inequality, and it gave us this 0.393. For the upper bound, we just used the observation that, of course, when you have this hull, okay, so the area of this hull is, of course, bigger than the area of the biggest inscribed circle. Okay, whatever this is, okay, if you those are the same if you're dealing with circle, but for any convex set, when you inscribe something inside it, it has area smaller than the whole thing into which you inscribed this circle. So only from there, and again Jensen, we got this upper bound of square root of 2 over 2. Okay, and then we because these were very simple observations, and then we wanted to switch to this different question, and this is like, how long do we have to wait until our convex hull attains a particular size? Okay, so what is the expected time until our Brownian convex hull reaches perimeter 1 or area 1 or diameter 1, circum or in radius 1? Okay, so actually all the random variables we were interested in, we were actually interested always in the expected values, and we managed to calculate 0 of those expected values. So all the expected values that we tackled, we just found bounds. Okay, so already now maybe you can get some idea how to improve, because there are only bounds. For everything we calculated, we only obtained bounds. Okay, and now we want to switch to this question. So expected time needed to reach a hull of particular size. Okay, and what will appear in many of the bounds there is some auxiliary lemma that I'll just, it's a sort of a result of interest on its own that I'll now briefly comment on, and you'll see later that it'll appear in our bounds. So again, we already defined what is the range of one-dimensional Brownian motion, and not only this range has been studied, also the inverse range. So this process, and notice not only this process range, like which is the difference between the running supremum and infimum of the Brownian motion, but all of our functionals, perimeter, area, diameter, they are all non-decreasing. Okay, maybe the trajectory goes back inside the hull for some time, maybe it doesn't change, but for sure those are all non-decreasing. Like the range of the Brownian motion, those are non-decreasing, and then you can define those inverse processes. Okay. And we will define these for all of our processes that we study. And here in this setting, we just denoted with theta. So we just look at the infimum over all t when RT jumps over this level. So we look when does this range reach some particular level, okay, level y for theta of y, okay? And what we wanted to know and what we used later, and I'll show you why and where, is if we have 2 different ranges, okay? So we want to know what is the expected time when the first of them hits value 1, okay? So we look at this, we have these 2 independent ranges, they are both growing, and as soon as one of them hits a particular value, okay, again from Brownian scaling, it's enough to look at 1. So as soon as one of them hits value 1, we look at how long did it take for this process to reach. So we look at the minimum of these 2 inverse range processes. Basically, it's, as I said, it's the expected value of the time needed until first one of these 2 range processes hits value 1. Okay, and we actually managed to obtain this closed formula for this thing, and we did manage to compute the integral explicitly, but numerically it gives this thing here. Okay, so in the same way, since all of our processes, perimeter, area, diameter, circum, and in radius, are non-decreasing, we can define the corresponding inverse processes. And basically what we want to know now is just the expected value of theta p, because then again we can just fix y to 1. So we want to tackle the expected value of theta p, which is the expected time needed until the perimeter of the convex hull is equal to 1, expected value of theta a, and so on and so forth. Okay, and now this looks a bit messy, but there is literally nothing else here than Brownian scaling. Okay, so each of these equalities in law is like one line calculation using Brownian scaling. Okay, this is the one I already commented on, that and it's the same for perimeter, diameter, circum, and in radius, only area behaves differently, okay, because it's homogeneous of order 2, not of order 1. Okay, so the pt has the same law as square root of t times p of 1. Also, this theta p of y has the same law of y squared theta p of 1, so that's why it's enough to study theta p of 1. And also there is this easy equality in law, again from Brownian scaling, that relates inverse process and the original process. Okay, I mean, like, all of these were already known for range, because people studied range like since a long time ago, and also the inverse range. There's a paper from 1985 by Imhoff where he computed the Laplace transform of the inverse range process. So they are all analogous. Okay, okay, for area is a bit different, but the relations for range are completely analogous to those ones here for perimeter, diameter, circumradius, and in radius. Okay, and now we use them again to get some simple results, and then we use some, I think, interesting constructions to get some other bounds. Okay, so when it comes to this time needed for perimeter to reach value 1, these are lower and upper bounds. And so now for several, for almost all of these quantities, we get lower bound. The best lower bound we managed to obtain was always somehow for free. Okay, why? Because from the previous slide, we know that theta p has the same law as 1 over p squared. Okay, and we know, and we then just use Jensen's inequality. Okay, because expected value of 1 over p squared is greater or equal to 1 over expected value of p, and then squared. And we know precisely the value of expected value of p, and that's how we obtain it. And that's the same thing. We will use the same thing for area, diameter, and circumradius, and we didn't manage to beat that. So only using this equality in law from the previous slide and what we already know about the expected value of the original things of the perimeter, diameter, area, circumradius, we got the lower bound here. And when it comes to upper bound for the perimeter, well, it was again Jensen, okay, and nothing much more clever than that. But we go back to this Cauchy surface area or Cauchy perimeter formula from 2D. So we know that the perimeter can be expressed as this integral of the parametrized range function, okay? And then we just interpret this integral as the expectation of the function w attacking a uniform random variable on 0 pi. Okay, then 1 over pi is still missing. But we just interpret these integrals as expectations of a uniform random variable on 0 pi, and then using Jensen in the same way, in the same fashion as we used it already before, we get this sort of bound, upper bound for 1 over p squared. Okay, and again we know this equality in law between theta p and 1 over p squared. So to obtain the upper bound on the expected value of theta p, we just use this upper bound on 1 over p squared, okay? So again, as we already commented in this one of the first slides, regardless of theta, when you start projecting, you always get something that the same in law, okay? For every theta, once you project your Brownian motion, you just get one-dimensional Brownian motion. So these things, 1 over w of theta squared, well, they all have the same law for all thetas, okay? So we use the same trick as the one you already saw when we were computing the expected value of the perimeter, and we end up with this thing here, and then we use the relation between the range and inverse range processes, which is the same relation as we had for perimeter, diameter, and those other functionals, and we end up with this upper bound of 1 over 2 pi squared. And actually for perimeter, those bounds are relatively tight, okay? So I think that's the best we got out of all the things we tackled. So they are relatively close to each other, okay? So, and when it comes to area, that's where we got a little bit more creative. So for the lower bound, nothing changed. We again use the same thing. We use the equality in law between theta a and 1 over a, and we use the Jensen, and we use what we know, and that's the expected value of a is pi over 2. But when it comes to the upper bound, so what do we want to do now? So we need to know that our Brownian convex hull really attained some area. So first we thought maybe it's enough just to look at the range 1 and range 2. Okay, so the range of the first component and range of the second component. But you can imagine that, for example, this line, which has area 0, okay, when you project it on the x-axis, it had some width. When you project it on y-axis, okay, you have something. So just by asking that both ranges are big enough doesn't necessarily give you area of a particular size. Okay, so our idea was, okay, so let us wait until our Brownian motion exits from a ball, okay? And then when it exits from a ball, we know that we have this line, so we have the radius of this ball, we have it in our hull. Okay, that's for sure, because we know that we have the starting point, we have the point where it hit for the first time, this circle, okay? And then, so we know that this is inside our hull. Okay, and now we want to spread in the perpendicular direction to attain some area. Okay, and so we then waited after that. So we first waited to exit the ball, and then we waited until the Brownian motion exited from this infinite strip, okay, of a particular length, okay, which reduces to just exit time of one-dimensional Brownian motion from some interval. And at that point, we knew that we have this triangle inside of our hull, okay? And we knew the this triangle, and we know the length of this side of the triangle, and we also know the length of the height. I mean, you know the height of this triangle, okay? So we knew that after it exits this ball, and then after it exits this infinite strip, we knew that at that point for sure there is a triangle of a particular area inside our hull. Okay, so that was the idea. But notice that what was the point of the first step, waiting until we exit the ball? What was the point of that step? The point was to get this segment of a particular, to be sure that there is a segment of particular length inside of our hull. But then we realized that we can obtain the same thing by waiting, and that's why we needed this auxiliary lemma that I showed. If we just wait until first one out of our two independent range processes hits a particular value, already then we know that we have a segment of that length in our hull. Okay, so I have some pictures here. So in the first step, we won't wait until we exit the ball. We will actually wait until at least one of our independent range processes, R1 and R2, hits a particular value. Like if, let's say, the radius of this ball is A, we won't wait until we exit the ball of radius A. We will just wait until at least one of these two range processes related to first and second component of our Brownian motion attains level A. Okay? Because when it happens, for sure we know that we have, so we know that there is some point here on this level and some point here on this level, so we have this type of segment inside our hull, okay? And its length is at least A, okay? So we really do have a segment of length at least A inside our hull. And then after this happens, okay? After this happens, then we just wait until we exit this infinite strip of with 2b actually, yeah, which amounts to waiting until one-dimensional Brownian motion exits this symmetric interval around the origin from -b to b. Okay, so it's again exiting from a ball, but for one-dimensional Brownian motion. And these are all known results. So what is the expected exit time of a Brownian motion from a ball, standard Brownian motion from a d-dimensional ball of any radius? It's always r squared over d, r squared over the dimension. Okay, so in our case, if you just look at the ball of radius 1, how long do we have to wait until we exit from the ball of radius 1? Well, it's 1 over 2, okay, which is 0.5. But as we showed in this auxiliary lemma, if you just wait until one of your two ranges hits value 1, it's less than 1 over 2. It was this 0.346 something. Okay. Yes. Okay, so what I said now is that, so first you want to wait, okay, let's say that A is 1. So you want to wait until you are sure that you have a segment of length 1 inside your hull. Okay, so one way to do that is to wait until your planar Brownian motion exits from a ball of radius 1. Okay, but because then for sure you know that the line connecting the center of this ball and this point where you exited is of length 1. Okay, but how long do you have to wait until your Brownian motion exits a ball of radius 1? Well, it's 1 over 2 because you are in 2 dimensions. Okay, but what we had before is, so another way to be sure that you have a segment of length at least 1 inside your hull is to wait until one of your two independent, like you look at this ranges. Yeah. Yeah. Maybe I said something wrong.
Yeah.
Sorry.
So
yeah.
One of two ranges, not coordinates, but ranges.
Yeah, ranges. Yes. Ranges related to coordinates. Maybe I said something, I apologize. Yeah. So you look at the range related to the first coordinate, to W1, range related to the second one, and as soon as one of them hits value 1, you are certain that you have a segment of length at least 1 inside your hull. And you don't have to wait 0.5 for that. You wait less, okay? So this happens on average sooner, okay? Expected value is lower for that, okay? And in the second step, we are actually just waiting until one-dimensional Brownian motion exits a ball of radius b, which is, again, b squared divided with dimension, which is here 1, okay? So we end up with this.
Before range hits B.
But which range?
Which range? I understand.
Yeah, it's like if you just somehow.
But if you have this tau A, tau B, and so
somehow, okay, so.
you mean that this segment is random? I mean direction. So
Yeah. You don't. Yeah. Yeah. So I mean, in theory, this could happen. Okay. So your Brownian motion could like look pretty much like this, and that's the time when you hit this. Let's say when this range attained value A. Okay. And if you now just wait until this other. So let's say this range attained value A, but the range related to the first component still didn't reach the value, or okay, this is the first one and the other one is the second one. If you wait until this one reaches some other range, I mean, it can still reach this range while your Brownian motion is just, wandering around this segment, okay? So just by waiting until one of your two ranges has a particular size, and then the other one has a particular size, that doesn't guarantee you any area within your hull. Your hull can still have area arbitrarily small.
assume that the range hits certain level.
Yeah.
Certain point. Yeah. Tau.
Yeah.
This is stopping time probably.
Yeah.
And this other point is a random variable.
Which other point? So here we exited. So here, let's say at this time tau A, this was the first time when one of our two coordinates hit level A.
Yes, but then they went that the first coordinate hit this level depends only on the past.
So after this, you would like to wait until the.
No, I mean that this segment, okay, it's random, but it depends only on past. And
Okay.
you take orthogonal direction, which is a random variable, and then you look the future increments that are independent of the past.
Yeah. I mean, but that's what we do. Okay. Yeah. Exactly. You take. I mean, we then really look at this perpendicular direction, yeah. And aha, you mean, okay, maybe I now understand. You mean now that we just, okay, yeah, this actually sounds reasonable. Okay, so I didn't understand you at first. So you don't want to wait until you exit this ball, but you again just want to wait until this second thing, now one-dimensional thing.
Yes. With random direction.
But do we then know that we have enough of a, I think we do, don't, or we don't?
So you fix
Yeah.
this direction,
And then this,
then
yeah.
you project orthogonal direction and look at the range in this direction.
Yeah. And once you have,
And if you have this, then it's perpendicular. So area of this is just this times this divided by 2.
yeah, okay. But then I'm worried a bit that, okay, let's say this happened now. And so what now? So we want to, so we want to look at this perpendicular direction and wait until we reach this.
Until the range in this perpendicular
Yeah.
direction is.
Okay, so we start from here. Yes, yes. This sounds good, yeah. Yeah, this sounds good. I think this is actually good. So I don't see now. Okay, we can discuss after, but it should be. Yeah, then I'm just wondering whether you can end up with something strange, but you shouldn't be able to. Yeah? I mean, even if you go like this and then you reach this range, then you know that you have you have this B still in this direction, and you can have, anyway, like you can split it in like two triangles, and yeah, and then okay, but will then the area of those two triangles will be like A times B over 2, I suppose. Yeah.
Perpendicular.
Yeah.
The same base. So 1/2 base times first 8 plus second.
Yeah. Okay. Okay. Then okay. Actually, yeah. Then it's like the same logic as in the first step. Yeah. Then okay. Yeah. So I'll check that. It looks good. Yeah. So we could probably do the same logic in the second step as we do in the first step. So that would actually have to reduce again the whole thing. Okay. Yeah. Thanks for that. Okay. Okay. So anyway, whatever. Then even if we do this other thing, which should be better, we then know that once this thing happens, and then once that this other thing attains range of a particular value, then we know that for sure we have a triangle of, for sure we have area, we have an object of area AB over 2 inside of our hull. So the moment where we for the first time hit this area is for sure something that happened before all of this happened, because at that point for sure we know that we have it. So the expected value of time needed to reach this area is definitely smaller than the expected value of like the sum of these two things that we waited for. And then we optimize. Okay, we know that AB over 2 has to be equal to 1 because we want to attain area 1, and then we just minimize the right-hand side with respect, because this can be expressed in terms of A. This is just A squared times this 0.346 whatever. This, okay, here is just B squared, or it should be something even smaller with the improvement, and then we just minimize this thing with respect to this constraint AB is equal to 2, and then we get the upper bound. Okay. And okay, maybe the most interesting part that I still haven't covered is just the inverse. So the by far the worst bound we actually obtain for the in radius, for the inverse process of the in radius. So these are just really straightforward. Okay, so for the lower bound we use the equality in law as we always do. For the upper bound, we just notice that as soon as one of these two independent ranges hits value 1, the diameter is at least 1. Okay? And for the circumradius, it's again the same. We use the equality in law. And here, okay, as soon as one of our two ranges hits value 2, the circumradius is at least 1. Okay. And then when it comes to when it comes to the inverse in radius process, then we have this horrible upper bound, but it's somehow still, okay, the one result that was auxiliary result on our way of obtaining this horrible upper bound, yeah, in radius. So small r is in radius, okay. So how long do we have to wait? Because now, okay, even with this idea we discussed, whether we look at this triangle as I showed, or as I said, or some rhombus or whatever the shape would be in your idea, we cannot control for the in radius, okay, because we maybe do end up with a triangle that has this side, in the like length of one, if its side is this one, and this is its height, but we never know whether this triangle maybe looks like this or so. So it doesn't affect the area, but it affects the in radius. Okay, so we really didn't know how to force any sort of a ball inside of our hull. Okay, so how to be sure that we will be able to fit the ball of any radius inside of our hull. Okay, so okay, let's just briefly comment. The lower bound is trivial. It's actually from the classical parametric inequality. So we know that when you reach area pi, well, your in radius, if you really reached a circle, is 1. But if you didn't reach a circle, but some convex body of area 1, then your radius is still less than or equal to 1. So for sure, this reaching area pi will happen before you reach in radius 1. Okay, so the time when you reach area pi happens before this time when you reach in radius 1, and it gives us this easy bound 2 for like lower bound for the expected value of the time that is needed for in radius to reach value 1. And for the upper bound, we actually used something in the spirit of this construction I just discussed for the area. And how did we do? Okay, so first, again, we just wait until one of the two ranges attains value A, because then we know that we have a segment of length at least A inside of our hull. And then after that, we, okay, not only we know that we have a segment of a particular length that we specified, but we also know that at that time, our Brownian motion is located at one of the endpoints of this segment, which is helpful here. And then we actually waited until, because then you can somehow restart the thing, okay, because of the Markov property, and then we waited until we exit something, our Brownian motion exited something that's usually referred to in the literature as radial slit plane. So how does this thing look like? So you have these slits, okay, you'll see on the next slide. You have this, but it should be in like black or something. You have these slits that are emanating from some circle of some radius that are like excluded from the plane. Okay, you look at the whole plane except from these like rays that start at some radius and then go outside. So this definition of the radial slit plane, you can define it for any n, and then it just determines the number of these slits that you will have on your picture. Okay, and actually people studied this radial slit plane, and they studied like this. What's the probability that once your Brownian motion hits one of these slits is on a distance less than r from the origin? Okay, so for us, what was important is, okay, we first waited until we are sure that we have a segment of length at least A inside of our hull. Then we somehow just rotated the whole thing. Okay, we put this point, this is the point at which we are sure we have a segment of length A. We put it in the origin, okay, and we put this segment to be just in this horizontal direction, and then we look from here, we wait until our Brownian motion hits one of these 6 slits. Okay, so we actually needed to compute the exit time of planar Brownian motion from this radial slit plane. So it was like the or hitting time of this slit. So we needed to compute the expected value of the time needed for planar Brownian motion to hit one of these slits. And this is what we developed as a result of a separate interest, okay? And I'll show what the result is. But then we know once we hit one of these, so either we will hit this one or this one, then those end up in the triangles of the same shape. And then either we'll hit this one or this one, that will also amount in the triangles of the same shape, and the same for the lower two. Okay, and so it means that we are sure once we hit one of these slits that we will either have this triangle A inside our hull, or triangle B, or triangle C. So for sure one of these triangles will be inside of our hull. And of course the worst case scenario, which is somehow clear for the picture, from the picture, but you can also calculate, the worst case scenario is this triangle A. This one has the smallest in radius. But for sure, after we waited for our Brownian motion to have the segment of length A inside, and after that, if we wait until we hit one of these slits, for sure we will end up with a convex hull that has this, like the inscribed circle of this triangle A, of a circle of at least that size will be in our convex hull. So a circle of at least this size will be in our convex hull after we also exit from this radial slit plane. Okay, and so we actually so we know that when all of this happens, we are certain that we have a circle with this in radius inside of our convex hull. Okay, so the time when we hit for the first time the in radius of this size happens before all these things happen, after this waiting for this minimum of two ranges hits a particular value, and after we wait until we exit from some radial slit plane. So again, we end up with some optimization problem here. But we, as I said, we don't really know what is the expected exit time from this. Yes?
Is there a specific reason you chose the 6 slit?
Yeah, we played with, that's an honest question. So what happens when you take some other, so okay, if you take 4 or less, you don't even have an infinite exit time. But you anyway, if you position this in a proper way, 4 sounds like it would maybe be a good idea, but the expected value of the exit time from the radial slit plane with 4 slits is infinite. Okay, but then we played with 5, but then it's not symmetric, so it's difficult to organize them to get big enough triangles. We tried with 8, and we optimized over the number of slits. Okay, it requires quite some work, but it turned out that 6 slits give us the best result. But that's a good idea. You can try with different number of slits. And then we actually managed to obtain the exit time, okay, of Brownian motion from this radial slit plane. And okay, there are many tricks when you're trying to compute exit times. There are many typical tricks. One of the tricks that can be used is if you know the expected value of this displacement, okay, at the time point when you exited, okay, when you know, for example, this. So we look at the expected value of this distance between origin and the point in which we hit for the first time one of these slits. If you know this, then there's like a relatively standard procedure to reach the expected value from there. And then again, we optimize over this in radius being equal to 1. And that's how we end up with this relatively bad upper bound. But still somehow with all these results in the background, it's like probably the most technical and difficult part of the whole paper. And we also ran simulations to actually estimate all the values that we wanted to calculate. So you can see how sharp some of the bounds are, okay? Because we simulated Brownian motion, and then we saw how good the bounds are, and you can pick your favorite one and try to improve. Okay, yeah, that's it for me. Okay. Yes. Yeah, those are here. Yeah. So these are our lower bounds we managed to obtain. These are the upper bounds, and then we just ran simulations to obtain the Monte Carlo approximations of all the expected values that we were calculating. We also ran since we anyway ran the simulations, we also estimated those known things, perimeter and area. So if it's okay to reason like that, I mean, we saw that on them it's on like 2 to we have order of precision is like 10 to minus 2, like we have 2 decimal places correct for perimeter and area, And for diameter, also the authors of this, McCredman and Shu, they also ran simulations for diameter. And for diameter, it's funny, but like the estimated mean with Monte Carlo simulation turns out to be like something 1.99, but really not 2, but slightly below 2. Yeah. Anyway, we did for all the values, we ran simulations and estimated the true values. Exactly. Yeah. So we actually played with 2 different ways of improving. Like, of course, you are simulating a continuous time process, but then of course you just specify the dt, yeah, the time scale on which you will be because you're basically simulating random walk, of course, and then you can either run with particular dt more simulations or maybe less simulations, but with a finer dt. And we actually realized, and then we really used the different several cores, and we ran simulations for weeks. And we took this dt to be 10 to minus 7. So the time steps in the simulations were 10 to minus 7. And we noticed as we improved from 10 to minus 5 to 10 to minus 6 to 10 to minus 7 that we pretty much got another significant digit correct with these improvements instead of just running 10 to minus 6 for much, much longer time. Okay, so the next step would be maybe to run with dt 10 to minus 8, but then we didn't have enough time or computational power or whatever. Yeah.
Missing maximum minimum. You can run it on a walk on parallel repeated or something like that.
Mm-hmm.
Then the simulation will be exact.
Mm-hmm. 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 Yeah, okay, so simulations for sure. Yeah. So I mean, none of us worked with any sort of simulations before, so it was just to get a feeling. But the simulation part, okay, I'm certain it can be better.
What is to get an idea? What is the value of getting lower and up? Can run an Monte simulation and get the result.
Well, those are just the approximations. So these are like still proven bounds, proven lower and upper bounds. I don't know. I mean, we did it for fun, but yeah. But still, I mean, you could say that for perimeter and area, also one can obtain those values with simulations. But then someone actually managed to do the analysis precisely enough to get these beautiful forms like square root of 8 pi and pi over 2. And we somehow hope that maybe somehow over time this will inspire someone else to some other idea, and maybe we converge really to the exact value for some other. So let's say that this was the motivation somehow, yeah. But you're right. Maybe this middle column is worth more than this left and right column here, yeah.
Okay.
Yeah, thank you.
Let's thank the speaker.